So it is my pleasure to welcome you all to the latest CQIQ seminar and to welcome one of our own. Many of you know Patrick Fraser, who's already an undergrad here and was doing a lot of fascinating work. Many of us are familiar with him. And he's now, if I understand correctly, in the inaugural class of U of T's master's program in philosophy and physics. And he's going to be telling us about a topic that really sits right at that boundary, what quantum mechanics has to say about the limits of knowledge, or maybe what the limits of knowledge teach us about quantum mechanics, related to the famous Wigner's friend paradox puzzle and recent work on that. So Patrick will be telling us about a no-go theorem for quantum knowledge. And let's all welcome him and interrupt him as much as possible to make sure to spread the knowledge around. Welcome, Patrick.
Thank you very much. So here, I'll just get some slides up. So can you see that all right? That's good. Cool. Awesome. Yeah, so thank you very much for the introduction and thanks for the opportunity to present this work here. This is definitely, I would imagine, one of the stranger presentations that you're going to see in the CQIQ seminar series, because it really does kind of straddle the line between physics on the one hand and philosophy on the other. And unlike a lot of talks at the intersection of those subjects, it's not a philosophy talk that draws on some physics or a physics talk that draws on a little bit of philosophy. It really does kind of, I'm going to have to dive deep into both disciplines, so bear with me. It might be a bit unusual if you're not familiar with this kind of framework from Forum. But yeah, so I'll get into things. I should also mention, of course, this is work that's been done in collaboration with some really wonderful physicists at the Institute for Theoretical Physics at ETH Zurich, namely Nuria Nerglieva and Lydia Del Rio, who are both co-conspirators on this work. So they are also a part of this. Yeah, so as the title indicates, I'm very interested in addressing questions about knowledge. The main issue that I'm interested in with this particular project is what does knowledge look like in a world that's governed by quantum mechanics? More specifically, what does knowledge look like in a world governed by quantum mechanics that includes multiple agents? Because it turns out when you have multiple agents that are all observing quantum systems and describing each other as quantum systems as well, there's a lot of issues that you run into with the consistency of the formalism and what the formalism tells you should do. So as an outline of what's going on here, of course, knowledge is the main philosophical concept that's playing a role in this. And so philosophers are very interested in epistemology and the study of knowledge very abstractly, but we want to be able to prove theorems, right? We want to be able to give concrete results for how we can quantify knowledge claims in the context of quantum mechanics. And fortunately, philosophers actually have developed formal frameworks for studying knowledge. There's this setting known as epistemic logic, which is an attempt to kind of formalize and mathematize claims about knowledge so that you can study theories of knowledge in an axiomatic way. And in particular, there's a very interesting result that comes up when you analyze epistemic logic that's called Fitch's paradox, which I'll have a lot more to say about shortly. So what I'm going to do is start by discussing epistemic logic very generally and the kinds of claims that one can make in that setting and how it works, give you an idea for the mechanics of that framework, and a bit about Fitch's paradox in particular. And then what I'm going to do is describe kind of what I mean by quantum knowledge as a particular kind of knowledge. That is, given the formalism of quantum mechanics and the way that physicists use quantum mechanics to represent the world, what sorts of claims does quantum theory allow one to make that you could call knowledge claims? And then what I'm going to do is I'm going to kind of move more, I'm going to lean into the quantum side of things. I'm going to look more directly at multi-agent quantum mechanics. So I'll start off with the traditional Wigner's friend scenario and describe how certain knowledge claims move about in the Wigner's friend scenario. And then I'm going to push things further to a much more advanced and complicated multi-agent scenario called the Frauchiger-Renner protocol, which is basically an extended Wigner's friend scenario. It's kind of like having two copies of the Wigner's friend scenario happening at the same time, where the two different copies are able to talk to each other. I'll clarify what this means. But this particular instance of extended Wigner's friend scenarios gives a fairly strong no-go result for how we should interpret quantum mechanics and when we can consistently deploy the formalism of quantum theory to describe the world. Having characterized a little bit about the upshot of the Frauchiger-Renner protocol, I'm then going to describe the epistemic implications for this procedure and how you can translate the no-go theorem given by Frauchiger and Renner into certain claims about what sorts of knowledge is possible for different agents in certain quantum scenarios. And from this, I'm going to leverage these kinds of epistemic implications from the FR protocol to get certain claims about how theories of knowledge in general have to be constrained if they're going to be adequate in describing knowledge possessed by quantum agents. And in particular, we're going to find that the strategies that are developed are sufficient to actually help dissolve Fitch's paradox. So quite ironically, we're able to take what is a fairly strong conceptual difficulty in quantum foundations and leverage it to get something that looks like a solution to a totally different paradox in a totally different area of academic exploration. So that's kind of the rough overview of how this is going to go. So I've mentioned Fitch's paradox a few times already at this point, so it's worth me mentioning kind of what the matter of fact is, and I'll describe it in a bit more detail shortly. But the idea is that if you have seemingly reasonable epistemic axioms, seemingly reasonable ways of characterizing how knowledge works, these lead to a very perplexing result, which basically says that everything that is true is known. Now, this should be kind of an unsettling claim, but this is a theorem that's provable from very minimal assumptions about knowledge. And I'll explain a little bit more about why this should be unsettling in a minute. But from this fact, we're then going to go on this journey through multi-agent quantum mechanics. And the main conclusion that we're going to draw from this is that if quantum theory is a source of knowledge, then knowledge obtained from quantum mechanical inferences does not satisfy the epistemic axioms needed to derive Fitch's paradox. So we can kind of throw Fitch's paradox away. And on the other hand, we're able to then impose hard boundaries for the kinds of theories of knowledge that are adequate for describing the knowledge possessed by quantum agents about quantum systems. So epistemic logic very broadly is a kind of tool that allows us to talk about certain kinds of things in a very formal way. So we want to be able to formalize statements of the form agent alpha knows phi, where phi is some sentence, or phi is knowable to agent alpha, things of this sort. And importantly, we want to be able to distinguish between what is known and what is knowable, because these are two very different concepts. There's things that I know, and there's things that I will learn in the future that I don't yet know, but which are knowable to me. These are two different concepts. And in order to have a formalization of these concepts that tracks these features, we also have to be able to accommodate modalities, notions of possibility and necessity. So how can we do this? Well, the basic procedure for doing this is just to write down a formal language. So a language that you can study and do logic with that has additional symbols that are interpreted in a particular way, such that it becomes expressive enough to capture these kinds of knowledge claims. So we're going to do this by introducing so-called knowledge operators into a language. So you've got a language of propositions, and then we're going to add to this language these operators that denote the knowledge of different agents. We're going to call them the K operators. And then we're also going to add these other modal operators, which are the necessity, the possibility operator given by a diamond, and the necessity operator, which is a box. And this is all very standard in philosophical logic. Now, to give a sense for how we're going to interpret these symbols, if I write down K alpha phi, that is meant to mean that agent alpha knows phi, right? Today is Friday is a fact. You can call that phi. If I'm agent alpha, I know that today is Friday, so K alpha phi is true, that kind of thing. But then we've also got other kinds of sentences like diamond phi, which means that phi is possible. If you're interested in the way that the semantics of this kind of logic will work, it means that it's true in some possible world, but possible worlds are not metaphysical things. They're just sort of a formal tool for extending how we assign truth values to sentences. We can also say things like phi is necessary, phi is true in all possible worlds, things like that. And then we can start to kind of braid these operators together and get claims like, if you write diamond K alpha phi, this means phi is knowable to agent alpha. So it's possible for alpha to know phi. And we can do other things, like we can start to braid together the various knowledge operators for different agents. So we can express things like agent alpha knows that agent beta knows phi, and things of this sort. But all we have right now are some symbols, right? That's all I've really given you. I wrote down some Ks with some subscripts, and I gave you a box and a diamond, and I kind of alluded to how they're meant to be interpreted. But we don't actually have any truth conditions for these symbols, which is to say that I haven't given any rules for when it's true that some agent has knowledge of some fact. Now, this might seem kind of limiting, but it's actually quite an important thing, because as soon as you start giving truth conditions for these knowledge operators, you're committing to assumptions about how knowledge works, right? So one standard assumption you might introduce would be something like, whenever something is known, then it has to be true, right? That's a kind of assumption you could introduce, but that's also something that you could have philosophical pushback against. And so you don't want to introduce axioms that characterize the truth conditions for knowledge operators unless you already have a robust theory of epistemology to begin with. So unless you already know what knowledge is meant to look like, you really shouldn't just arbitrarily introduce axioms for how knowledge behaves. That said, we want to be able to consider particular schemes of axioms for how knowledge behaves, and we want to be able to kind of test different kinds of theories of knowledge. So we can do that, and in particular, we're going to try a specific kind of axiomatization for knowledge. So one option is known in the context of epistemology and philosophical logic as constructivism. And constructivism is just this view that everything that is true is in principle knowable. Now, this is a contentious view. This is not a view that everyone buys into, and for good reason, right? Because especially when you think about quantum mechanics, it's not at all clear that just because something is true, it can be known. There'll be more to be said on that later, but for a moment, you might recall, for instance, in the classic EPR paper, when they describe elements of physical reality, there's this question about whether or not quantum mechanics is a complete theory. For quantum mechanics to be a complete theory is for every element of physical reality to have a counterpart in the theory that can in principle be derived. If quantum mechanics is incomplete, then not all truths are knowable in a certain sense. So this is a contentious view. But in the context of sort of traditional epistemology and certain aspects of how we think about mathematics in particular, this is quite a reasonable view to adopt.
Patrick, can I jump in for a second?
Yes,
that bit
please.
about the completeness versus knowability actually confused me. Of course, that wasn't how EPR defined element of reality. I could imagine, either the position or the momentum of a particle being knowable without being in the theory. They could be known if you measure them. They may not be simultaneously knowable, but either one of them was knowable, just not known a priori.
Right. So yes, so that's a good point. Yes. So I guess that's a good point to kind of bracket for later, because the completeness of quantum mechanics is, of course, a contentious issue for a lot of reasons. And how we actually map knowledge claims in quantum mechanics onto this kind of logical framework is going to be a little bit subtle. And I think it's possible to give an account of what completeness of quantum mechanics would look like in these terms, but I'm actually not satisfied that I have a very well articulated one at the moment for this particular issue.
That's all right, but I think to get the definition straight, I want to make sure, if there's something that isn't in the theory, but I could measure it.
Right.
Are you going to consider that knowable? Or when you say knowable, you mean things I could have written down before doing a measurement, or a set of things that I could know all simultaneously?
Yes. So how this is going to play out is I'm going to call something knowable in the context of quantum mechanics. If we take quantum mechanics to be kind of the be-all, end-all, absolute theory of how the world works, which is, of course, a suspicious move anyway. But if we do that, then to be knowable would be to be able to predict something with certainty. And to be known would be to see it on a detector. And so there would be a discrepancy between what's knowable and what's known. At least there would seem to be a necessary discrepancy there. Yeah. Does that make sense?
We may come back to it, but that's
okay.
Good for now. Thanks.
Yeah. Yes. So kind of the more ordinary intuition for this constructivist hypothesis. So we formalized this constructivist hypothesis as an axiom that says if something is true, then it's possible for some agent or for any agent to know it. Now, particularly you would want to say for some agent to know it, but if all agents can trust each other and can talk to each other, then if one agent can know something, they can share it with other agents and knowledge can propagate in a particular way. So this is the axiom that we introduced to motivate this constructivist hypothesis. If you think about things in terms of mathematics, you might encounter something like a mathematical theorem in some framework that is complete, Pache, Gödel completeness theorem stuff. We've got this notion where to be true is to have for a theorem to be true is for there to exist a proof of that theorem. And if there exists a proof, it's possible for a mathematician to write the proof down. And since it's possible for a mathematician to write the proof down, it's possible for them to come to know that fact, that theorem. However, they might not write it down. So it's only possible for them to know it. They don't have to know it, right? So that's why, especially if you're concerned with the foundations of mathematics, constructivism becomes kind of a reasonable view to adopt for motivating what knowledge is. And actually, a lot of constructivists would use this as a way to define truth rather than knowledge, but that's a side issue from a different debate. So this is one axiom that we can entertain about how knowledge works. To be true is to be knowable in principle. Now, there's another axiom that I want to consider as well, and this one I hope should be even less contentious. So this is a claim about the internal continuity of the knowledge that a particular agent has. So we might want it to be such that we prevent the following from being the case. We don't want any agent to be allowed to say, I know the following is the case, phi is true, and I do not know phi. Because it would seem that if you know that phi is true, and you are in a position to say that you know that phi is true, you shouldn't also be in a position to say that you do not know phi. That would seem to be just not how knowledge works. Now, of course, you can give objections to this, but this is a fairly standard axiom to suppose. It's called the epistemic version of Moore's paradox, or I guess the solution to the epistemic version of Moore's paradox. And we formulate this as a continuity axiom of the following form. So this is just how we formally write down this axiom, and we just say, if K genuinely represents knowledge, then K has this property generically. So this is kind of, these are the two kind of philosophically loaded axioms that I'm going to adopt or entertain more correctly, because we're going to find that there's reasons to push back against them in what follows. And it turns out that these two axioms alone are sufficient to derive Fitch's paradox, which I'll get to in a moment. We're also going to look at two weaker axioms as well. And these ones I am going to kind of suppose to be fixed and set in stone, but they're quite minimal assumptions. So the first one is a distributivity axiom, which says that if I know phi and I know psi, then I know the conjunction phi and psi, right? And in particular, this is actually quite a weak axiom because I'm only going one direction, right? I'm not saying that you can decompose conjuncts and that your knowledge is somehow able to decomplexify itself in some non-trivial way. Really, I'm just saying if you know something is the case and you know something else is the case, then you know that both of them together are the case. So this is the weaker version of distributivity. And in general, there's very little pushback against this. There's not a lot of, I think Timothy Williamson has an objection of some form against one version of this, but I think that requires the biconditional going the other way. Anyway, so this is a fairly uncontested assumption about knowledge. And then the other one, yes.
Can I ask a question about that?
Yes.
Where does time fit into this picture?
Right.
Because if I measure spin Z and then spin X, I do not know that it's both.
Yes. So, yeah, so this is a good point. The way that I would say that is that what I'm doing right now, all of this stuff is kind of static. So this is kind of describing knowledge and knowability at one moment in time. And if something is knowable, then if you then look at the sort of matters of fact about what's known at a future point in time, they might look different. So if I carry out, say, a position measurement, and I have knowledge of the outcome of the position measurement right now, then at another point in time, I might carry out a momentum measurement, and at that other point in time, I would have knowledge of the momentum outcome. But at that point in time, I would no longer have knowledge of the position outcome. And so I would not have the conjunct, if that makes sense. Like,
right, okay, so that sounds like you need some kind of measurement disturbance trade-off.
I mean, to get to that claim that I just made will require a little bit more of an analysis of the propositional structure of quantum measurements. So there's this kind of Birkhoff von Neumann propositional logic that's given often when people describe quantum logic. And I think what you're going to end up I mean, that's okay. That's typically only really posed for finite dimensional systems, but you can talk about coarse grain measurements and so on. And I think what you'll end up getting is that the way that we're going to describe what knowledge is in the context of quantum mechanics is going to be such that having knowledge, like just in virtue of commutation relations, I think that there should be a footnote there, because I haven't actually given a full argument for this, but I would imagine that you could say something like, if you are in a position to know exactly, like to know with certainty that some measurement outcome will obtain for some particular observable, and if you have a non-commuting observable, you're not in a position to predict with certainty what the measurement outcome of that other observable will be, and so you're not in a position to make knowledge claims about the outcome of those measurements in this very strict notion of knowledge claim, where it's really about absolute certainty of measurement outcomes.
Yeah, Patrick, if I can jump in here, because I get the feeling that Hilary and I are having the same misgiving here. And I do think it just comes down to definitions. I think when you say knowability, you seem to mean it from a very mathematical, theoretical perspective, whereas to some of us, knowability means I could know it, I could measure it. And I really think when you talk of knowability, you mean given a theoretical description of a quantum state, could that contain enough information for me to know X, Y, or Z? You don't mean, could I do a measurement after which I would have a different quantum state and I would know something else? So we're always talking about knowability based on a quantum state, not based on what I might go out and measure.
Yes, exactly. Okay. So knowability is going to be cashed out in terms of what the formalism alone allows me to predict with certainty. And then what is actually known is given presumably by the outcomes of actual measurements. And there is an interesting question about which measurements are possible and which measurements are not possible, and which kinds of facts I could in principle acquire knowledge of experimentally. But the notion of knowability at issue here is really at the theoretical level of what does my state description encode? Yeah.
Okay.
Does that help?
Yeah, I think it's probably best if I don't derail your talk. We can talk about it later.
Cool. We'll get back to this soon. So there's only one other axiom actually that I want to introduce for knowledge, and this is an axiom about the non-contradictory nature of knowledge. That is to say, no agent should have knowledge of a contradiction, properly speaking. Now, this is actually an interesting assumption. It's actually weaker than you would expect, because I'm not here requiring. This is a very minimal system that I'm developing here. I'm not actually requiring that things that are known are true. I mean, that's possible. That's something that you might like your system to have, but I'm not actually requiring that. That's kind of, even if you disagree with the idea that to be known is to be true, that's irrelevant entirely to these considerations. This is a very weak formal system for describing knowledge. All that I require is that the knowledge that somebody possesses is internally consistent with itself. Now, which is to say there's no moment at which someone has knowledge of a contradiction. What this is going to look like in the quantum context is if I do actually carry out a measurement and I observe an outcome of that measurement, I'm only ever going to observe one outcome. I'm not going to observe distinct outcomes. Does this make sense? Like, I'm not going to, if I do say a spin measurement, I might find spin up or I might find spin down, but I'm not going to see both spin up and spin down. So this is kind of what the non-contradiction assumption is about. It's just to say there's internal coherence with what I know, which need not require there to be in this kind of coherence with what's actually the case, just with what I know.
Okay, can I raise another question?
Yes.
Sorry to be so difficult. There's something called Luda's rule, whereby you can do a partial measurement and you get partial information about the state, but the set of states that are consistent with their outcome can include states that are themselves mutually orthogonal.
Right. So this is a good time to mention that I'm going to qualify what constitutes a knowledge claim in a very particular way, which is I'm actually going to restrict myself just to projective measurements. Now, that might seem like a limitation of this kind of formalism, because of course projective measurements are not even close to the full sophistication of the kind of measurement schemes that are used in actual experimental physics. But it turns out that you're able to get these interesting counterexamples that I'm going to leverage for these purposes, even just using projective measurements. Yeah.
There's some disagreement about how you define projective measurements, because you can argue that Luda's projection is a projection, it's just onto more than one state. So it's more than, instead of onto a one-dimensional state, which you get with a rank 1 projector, it includes a subspace which has higher dimension.
Sure. So
this might be just nitpicking about definitions, but
yeah. So one way to view that would be to look at the kind of knowledge claim that you get out of such a measurement. So if you do a projective measurement onto some higher dimensional projective subspace, then you could look at that as what you know is the conjunct of basis elements that generate that projective subspace. So you know, or sorry, not conjunct, disjunction. You know, for instance, the first state or the second state or the third state. You get knowledge of the disjunction of those things, and that's the kind of thing that you get knowledge of when you carry out that kind of measurement. Does that help?
I'm not sure, but I also let's not derail your talk.
Cool. Okay, so we've got some axioms on the table, and this is all right now, like, this is just a kind of basic language about how to talk about knowledge in a very particular way. And these two assumptions on the screen right now I take to be hopefully fairly uncontroversial. You can give accounts that I take to be reasonably convincing that even in the context of quantum mechanics, these are typically not the points of suspicion. It's really the first two axioms that I mentioned that are going to be the ones that cause conceptual difficulties. But then we get this theorem, which only requires these first two assumptions, the constructivist hypothesis and this knowledge continuity assumption. And it's just a theorem that follows directly from these claims, which says that if something is true, then it's known by an agent, right? So if all facts are knowable from the constructivist hypothesis, then actually all facts are known. And now this seems completely outrageous, right? So you might consider, as an example, something like a coin toss, right? If I flip a coin and I catch it in my hand and I don't look at the outcome, there's a matter of fact about the outcome of the coin flip. And if I were to open my hand, I would see the outcome. So that outcome is possibly, like, that's knowable to me. It's possible for me to know it. But at the moment, it would seem as though I don't know the outcome of that coin flip, and it would seem as though nobody else knows the outcome of that coin flip. So here's an instance. Yeah.
Who or what is an agent? Because I mean, there's a school of thought in interpretations of quantum mechanics. It's usually attributed to Wheeler, of saying information is physical. Something is true, then there is some subsystem in the universe that knows it. Although it isn't necessarily human or anything like that, it could just be another particle.
So here I'm taking an observer to. I'm being kind of intentionally non-committal in certain respects, but I'm taking an agent to be some physical system that is capable of interacting with another physical system in such a way that we would call that interaction a measurement. What do I mean by that interaction being a measurement? Something of the form, the memory of that agent system becoming entangled with the eigenstates of the observable being measured by the measurement that they're purportedly implementing. This is, of course, like it's very hard to pin down a good definition of a quantum agent, and that's part of the problem.
I think the property of having a memory is essential into what makes an agent. And I think maybe I'm circling back to the earlier question about the role of time in this. I suspect maybe you're going to get to all of this stuff later, and I'm just jumping the gun. Anyway. Okay.
Hopefully, I'm going to get into quantum mechanics stuff very shortly. So hopefully things will get a bit more clear. Because this is definitely a very strange way to approach a talk for a quantum information audience. So we've got this bizarre result called Fitch's paradox, and in the context of philosophical logic, this caused decades of turmoil. There were tons of papers that have been written about this, trying to make sense of it, and frankly, it's a bit of a mess. And there's not, as far as I'm concerned, any kind of consensus about what constitutes a good way to resolve this paradox. So now we're going to switch to quantum mechanics, and I'll hopefully be more explicitly clear with what I'm trying to say when I talk about quantum knowledge. So a guiding principle that we're going to adopt here, because of course, there's a question: can scientific theories give us knowledge about the world in any way at all? Well, if you say no, then the rest of the talk is complete nonsense. But if you say yes, then there's another question, which is which scientific theories can give us knowledge about the world? And we're going to have this guiding principle that says, well, quantum theory better well be one of those theories that gives us knowledge of the world. And part of the motivation for this would be to say something like quantum theory is so empirically successful or so well confirmed in various regimes or something of that nature. There's so much good reason to accept quantum theory as a good description of reality that if it allows one to predict some measurement outcome with certainty, then one is warranted in calling that prediction knowledge. More explicitly, again, I'm just talking about projective measurements, but if you've got some system that's in some state and some observer alpha that's positioned to carry out a measurement on that system using some projective measurement scheme, then the propositions that we're interested in are propositions of the form outcome I will obtain. And we would say that that kind of proposition is knowable if and only if, just from the Born rule, the agent is able to predict with certainty that that measurement outcome will obtain. So this is to say, if just from the state description, the agent is warranted in inferring that some measurement outcome will happen with certainty, then that agent, then the proposition outcome I will obtain is knowable to that agent. Now, I say knowable because whether or not that actually becomes known is to a certain extent dependent, for instance, on whether or not they bother to carry out the measurement or whether or not they even bother to carry out the derivation using the Born rule to get this probability. But this is kind of what we have in mind with this. Now, why do I restrict to projective measurements? Well, I mentioned that this sort of thing of outcome I will obtain being a proposition. It turns out that since the 30s from Birkhoff and von Neumann, there's a very well understood framework of quantum propositional logic on a non-distributive lattice that has very well understood mathematical properties, and it's very precisely articulated. When you switch away from PVMs, even just to POVMs, there are approaches to doing quantum logic and quantum propositional logic, but it becomes a lot more difficult, and it's not actually so clear what the intended underlying propositional logic looks like. And it's not, and there's multiple competing schemes that try to give accounts of this in different mathematical languages. And so things get very complicated when we move away from PVMs. So for our present purposes, we're just going to talk about projective measurements in this setting. And when we do so, there is a very well-defined, very well understood underlying propositional logic that we can supplement with these epistemic notions.
Hey, Patrick, do you mind if I ask a quick question about some of the definitions? I think maybe these are basic questions that maybe, well, hopefully some other people, well, hopefully I'm the only one confused, but in case anyone else is confused, maybe it will also be helpful. But just going back one or two slides about the non-contradiction thing. Yes. Yeah, so I think the way that I would read this bottom statement, and this clearly means that I'm not understanding something about what we mean by knowledge or truth, is that it seems like something and its contradiction, like, don't I just know that this is false? Why isn't that knowledge?
Okay, so yeah, so how you would read this is saying that it's not the case that agent alpha knows phi and not phi. So there's no instance in which any agent knows something to be true and also that same thing to be false, right? So it's kind of like if I, if I just at a kind of in a classical level, if I look outside and I see that it's raining, I know that it's raining, and because I know that it's raining, I necessarily don't know that it's not, like I'm not in a position to know that it's not raining.
So isn't it an even stronger statement? Because you pointed out that your distributivity axiom is not reversible. So you could have just negated the left-hand side of the upper thing, saying I can't know phi and and not phi, and no, not phi. But instead, you also said I don't know that conjunction, which you've argued isn't an equivalent thing here.
Well, okay, so what I can do, so you're absolutely right. If I were to contrapose the distributive axiom, then what I would get is, on the left side of the arrow, I would get this non-contradiction statement, and on the right-hand side of the arrow, I would get that it's not the case that alpha knows phi and knows not phi, and that's fine. That's so the really all that this says is if you don't know a contradiction, then you don't on the one hand know something to be true, and on the other hand know it to also be false. So it's not actually all that strong to apply distributivity to the non-contradiction axiom. It ends up actually being a fairly weak theorem to get. It doesn't really commit you to anything stronger. If that, I hope that kind of makes sense. Yeah.
Maybe there's something with the notation that's confusing me, or some rule of the algebra that is tripping me up. But inside the parentheses, I see phi and not phi. And to me, that's just false. And so it seems like this is just saying K alpha of false. It seems like that should just, is there is there a step that I'm missing there?
So what you don't, so you would, if you take, on a very classical view of logic, you would say, well, this contradiction just has to be false, right? And since it just has to be false, then there should be no instance in which anybody knows it to be the case, right?
But you didn't assume that we don't know falsehoods, if I remember correctly.
So this is kind of what you get if you, we don't know things that are, if you obey kind of a classical logic, the claim would be that you don't know anything which is necessarily false, right?
Don't know. Okay. So this is good, because I think something about my understanding of what you mean by knowledge was messed up. So I think that's what it is.
Okay.
So when you say you know something, you're basically only allowed to know things that are true. Is that that's what you would like, yes. But just the way that this is set up, if you adopt that view, then this is a very natural thing to commit to. But you can commit to this even if you don't adopt that view. And the point is, this is just a very weak system for describing knowledge. So we don't we take this. If you assume that knowledge is everything that's known is true, which is an assumption you can make, then what you end up with is that this kind of follows very immediately. But you can assume this feature without necessarily supposing that everything that is known is true.
I think, to be clear, Noah, you're talking about things that you and I know about our standard definitions of knowledge and so forth, while Patrick is trying to build up an axiomatic system. So nowhere so far has there been an axiom that if you know something, it is true, or if something is false, you don't know it. We would all like that to be the case, but Patrick is saying he doesn't even need that assumption. He makes the assumption that you can't know a contradiction, but he hasn't built in axiomatically the assumption that you can't know a falsehood that may or may not arise later.
Okay.
Cool. So let's now get into some quantum mechanics. So with all of this kind of in the background now, let's start to talk about quantum mechanics. So just with this very elementary definition of knowability, it would seem that if I'm just concerned with one agent observing one system, I've got a fairly weak way of talking about knowledge, but I also kind of have some conditions to determine when knowledge claims are true or false. So let's instead look at multi-agent scenarios, because these end up being much more interesting. So we're going to look at the classic Wigner's friend scenario. We're going to suppose that there's an experimenter that's measuring a qubit in a lab, and then there's some external observer who knows that this measurement has occurred but doesn't know its outcome. So this is a classic thought experiment that comes up often in quantum foundations. This is pictures that Nuria made that I'm going to use for this. And so the way that this typically works is we've got, on the one hand, the friend who we'll call Alice in a lab, and we've got Wigner outside of the lab. And Wigner knows that the measurements happened, but doesn't know the outcome. Alice sees a definite outcome. And if you look at Wigner's description of what's going on inside the lab, if Wigner traces out, so Wigner sees Alice's memory being entangled with the qubit, right? Wigner sees that they're in an entangled state that's a superposition of the qubit being spin up and spin down, and respectively Alice's memory of having seen the qubit be spin up and spin down. And so for Wigner, there's no definite outcome that's observed, and for Alice, there is a definite outcome that's observed. Now, this played a big role in how people went about trying to interpret quantum mechanics for a lot of reasons. And it turns out that there's very interesting debates to be had about, whose description of the world is actually correct and so on and so forth. But we're not even really considering, like, with this present issue, we're not actually so interested in, what we're not worried about who's right about their description of the world and who's wrong about their description of the world. We're concerned about what do they both know. So if we look at the Wigner's friend scenario, there's a few fairly straightforward inferences that we can make about the knowledge claims that are warranted. So we're going to write down this sentence. So this is not a quantum state. This is just a sentence that describes a measurement outcome that says the spin is up. And let's just suppose that in actuality, when Alice makes the measurement, she sees spin up. Then we get the following knowledge claims. On the one hand, we know that the fact that it's spin up is knowable to Alice. If Alice reads her detector, she'll see that it was spin up. And if we look at Wigner's knowledge claims, we'll see that because for Wigner, the state description after the measurement is given by if he traces out Alice's memory, the state description is given by a mixed state of spin up and spin down. On the one hand, it's not possible for him to know that the outcome was spin up, but it's also not possible for him to know that the outcome was not spin up, right? He just has no knowledge whatsoever about the outcome of the measurement in particular. So these are very basic claims that you can make. This is not supposed to be anything super deep at this step. And then if Alice does in fact look at her detector, she'll say, like we would also say that not only is it possible for her to know this outcome, but that she actually does know this outcome. Okay, so this is all well and good. Hopefully the evaluation of these kinds of knowledge claims in the Wigner's friend scenario where we just have two agents is not too contentious. I mean, there's a lot of controversy to be found in Wigner's friend for sure. But most of that has to do with how we interpret, whether or not the scenario is well posed at all, what the actual true facts about nature are when we describe the world in that way, who's right and who's wrong, things like that. But for our purposes, we're just concerned with the kinds of knowledge claims that these agents can make. And those turn out to be actually not too hard to make sense of. So with that in mind, let's make things a lot more complicated and switch to the Frauchiger-Renner scenario. Now, the Frauchiger-Renner scenario is a lot like the Wigner's friend scenario, except for now there's 4 agents and there's 2 different laboratories. And we've got the first pair of agents going about a Wigner's friend scenario and the second pair of agents going about a Wigner's friend scenario, and they actually exchange qubits in between in this protocol. And it's really quite a mess, to be perfectly frank. It's really interesting, but there's a lot of details going through the protocol and how exactly it works. So I'll give a rough sketch of it, but I hope you won't hold me to the details of the protocol. It's been discussed extensively in the foundations literature, and generally it's viewed as the conclusion of it is well formed. It's just hard to interpret. So I'll give you a rough sketch of the Frauchiger-Renner scenario. But basically the idea is this: we've got, again, like I said, these 2 Wigner's friend setups. So we're going to call our characters Alice and Ursula, and then Bob and Wigner. And what happens is we start off with Alice flipping a biased quantum coin, or it's a qubit, but we've got this coin that starts in an initial biased state, and she carries out a heads tails measurement on her coin. And then if she observes heads, she prepares a different qubit, S, in a spin up state. And if she observes tails, then she prepares it in this 90-degree rotated state. And then what she does is she sends this qubit that she's prepared to the lab of Bob. So you'll remember so Alice has this quantum coin that she flips to determine how she'll prepare the qubit, and then she sends the qubit to Bob in the state that she's prepared it in. Then what we do is we look at Ursula, and Ursula carries out what's called an OK fail measurement on the lab of Alice, where OK is, so the OK fail basis is given by this kind of superposition basis, this 90-degree rotated basis from the heads tails basis of the coin. And this is really a measurement that Ursula is carrying out on on Alice's memory of the coin flip. And then Wigner is going to carry out a similar OK fail measurement on the lab of Bob, where we've got likewise this kind of rotated basis for the measurement. Now, this is a complicated scenario. And what they then do after describing this scenario is they go through and they demonstrate that from different matters of fact about the scenario, given what certain measurement outcomes are, the different agents are capable of making inferences about what they expect the other agents to see, right? So as an easy example of this, let's go back to here. If Alice sees a spin, or if she observes a tails outcome when she flips her coin, then she knows that the state that she's prepared is of this form that when she sends it to Bob. And because of that, she knows that when Wigner carries out his OK fail measurement, he'll get an outcome of fail, because the basis of this is exactly what it should be. And I think, sorry, these subscripts should be, I think, B. But anyway, so, or S. So, okay, it's a complicated protocol. I would appreciate if you don't press me too much on the exact inferential steps that go through to get the conclusion that they draw. It's all very explicit in their paper and it's very complicated. But the upshot of it is that with a non-zero probability, I think it's probability 1/12, Wigner will observe an OK result, despite being able to predict with certainty from what other agents know, or from what he infers other agents know, that he should observe a fail result. So, and in fact, all of the other agents are also in position to predict that Wigner will observe a fail result on that particular run. So conditioned on different outcomes that they already see, everyone's in a position to predict that Wigner will see OK, but what will actually happen is Wigner will observe fail. And they predict these with probability 1. So these would seem to constitute genuine knowledge claims on the parts of all of the agents, because they're predictions they make just from state descriptions that have measurement outcomes of probability 1. But nevertheless, what we as an external observer will predict to be the case is that in many instances, the actual measurement outcome will not be OK. It'll be a failed measurement outcome. And this seems like a contradiction. And this is what Frauchiger and Renner take to be kind of a very deep result about how we use the quantum formalism. Now, generally speaking, the way that people interpret this now is that if you just naively deploy the textbook formalism of quantum mechanics that you find in your favorite book, without any supplementary information about who's allowed to apply which steps and when, if you have no notion of where to put Heisenberg cuts and things like that, then that's when you get a contradiction. So the idea is that the quantum formalism on its own is insufficient for describing its own consistent use. You need something additional to that, some sort of interpretive content that tells you how and when you're allowed to apply different features of the formalism. And that's, of course, a non-trivial issue. Now, they derive this result from 3 assumptions. And these 3 assumptions are basically of the following form. The first one says that agents are allowed to use quantum theory to reason about the world. In particular, they're allowed to use the Born rule to attribute probabilities to their expectations. The second one is a single outcome assumption, which says that after performing a measurement, agents only witness a single outcome. This is the idea that, if you carry out a measurement that has n different output ports, you've got n detectors, only one of those detectors will click in a given run of the experiment. Setting aside issues of coincidence counts and so on, where you might have multiple systems that are being measured at once. If you're measuring one system in one measurement scheme, you'll only have one outcome of that measurement actually being realized in any instant. That's the single outcome assumption. And then there's this C assumption that says that agents can combine their predictions with those that they predict other agents will make using a kind of classical logic. Now, these are, of course, somewhat loaded assumptions. And importantly, if we look at actual interpretations of quantum mechanics on offer, we find that most of them do violate one of these assumptions. So the upshot of the Frauchiger-Renner scenario is that you get this contradiction, which they take to then imply that those 3 assumptions cannot be upheld all at once. So one of these assumptions has to be violated. If you look at actually existing interpretations of quantum mechanics, most of them, it turns out in the literature that ensued after their paper came out, most of them can give a reasonable description of which of these is violated on those interpretations. Spontaneous collapse theories violate Q because they don't, or well, okay, there's also, modifications of the quantum formalism typically violate Q. Many worlds interpretations, Copenhagen a la Heisenberg violates the C assumption. The relational quantum mechanics framework seems to violate the C assumption. I think quantum Bayesianists have argued that they either violate Q or C. Some many worlds people have argued that they violate S, but I think a more reasonable view is that they violate C. That you can give accounts of all of this, and people have done so.
Patrick, I'm just going to jump in to say that although we're not going to want to cut you off, it's noon, and I see some people have already had to leave, and that may accelerate. Yes. So
okay.
If there's a chance you can get to your main point in 5 minutes or so, that would be excellent.
Perfect. Noted.
Apologies.
Yes. No worries. It's all good. There was a lot of discussion. So what we can, the main upshot is that we can formalize the Frauchiger-Renner assumptions as knowledge claims. So the first one ends up being a claim about the possibility of certain things being known. The second claim ends up being a statement about the single outcome assumption is basically just saying that you can't have non-contradictory knowledge. So it just goes right up against the non-contradictory knowledge assumption. And then the C assumption is actually quite interesting. If we formulate it in this epistemic language, it becomes this claim that, if an agent beta knows that an agent alpha knows something, then agent beta is warranted in knowing that thing themselves. And what we basically do is we can go through each of these assumptions and we can see what the ramifications are in the epistemic logic framework if they're violated. So if Q is violated, we right away find that this contradicts the constructivist hypothesis, or in principle, the knowledge continuity assumption. There's another way of doing that. If S is violated, then we find by an application of the distributive hypothesis that this contradicts the non-contradictory knowledge assumption. And then if C is violated, this is actually the really interesting one. It's really difficult to figure out exactly where things go wrong, but you can actually prove that this requires you give up at least one of these four assumptions that I've stated. The proof is a bit of a pain. I'm not going to talk about it at all, but you can prove this. You can derive this contradiction from the C assumption or from a violation of the C assumption. And so the upshot of all of this is that Frauchiger and Renner kind of establish via a reductio argument that the framework of quantum mechanics implies that not all three of these assumptions about quantum mechanics can be upheld. In a totally separate area of discussion, Fitch further established that from the constructivist hypothesis and the knowledge continuity assumption, Fitch's paradox arises, which we take to be problematic. And what we do in this work is we derive theorems using the formalization of the QS and C assumptions described to demonstrate that that any violation of these assumptions entails a violation of at least one of these epistemic axioms. And so we can summarize these results, and this gives us kind of a strict kind of limitation on the allowed epistemic axiomatizations that we can have that will be compatible with quantum theory. So if you violate the Q assumption, you have to give up either the constructivist hypothesis or knowledge contradiction, or sorry, knowledge continuity. If you violate the S assumption, you have to either give up on distributivity or the non-contradictory knowledge assumption. If you violate C assumption, then you have to give up one of these four assumptions. The main upshots of this are that if you reject the single outcome assumption, you're immediately pushing back against what we take to be the least controversial axioms for how knowledge works. And since we take these to be so reasonable, in order to object to them, you have to, either you can look at it as we have principled grounds to deny interpretations of quantum theory that violate S, or any interpretation of quantum theory that violates S has to tell a compelling story for why one of these two epistemic axioms fails. And then on the other side of things, if it's Q or C that's violated by a particular interpretation of quantum mechanics, then we actually have grounds to say that the axiom is required for deriving Fitch's paradox cannot be sustained, and so you don't have to worry about Fitch's paradox anymore. Anyway, there's some more stuff that comes up as well, but kind of in summary of everything, if quantum theory provides us with knowledge, our theories of knowledge must be able to accommodate quantum theory. Epistemic logic allows us to formalize and axiomatize theories of knowledge. However, compelling systems seem to exhibit these pathologies of Fitch's paradox that all truths are known. If we take the Frauchiger-Renner paradox seriously, we can find that it imposes constraints on the allowed axiomatizations of knowledge. And in particular, most interpretations of quantum theory allow us to deny Fitch's paradox. There's, of course, more points that are interesting to talk about, but I'll wrap it up there. Thank you all very much for your attention. Sorry for going over on the time, but yeah, thanks a lot.
Thank you. That was really a fascinating and provocative talk. Much applause. Sorry we can't be thanking you in person. And I know the time was actually perfect. Let me open the floor to questions.
I guess, can we just jump in?
Please jump in.
So this is based on the sort of account that you gave on what knowability is when you wanted to apply it to quantum mechanics. So basically, correct me if I'm wrong, but it's if you can use the Born rule to get a probability of 1 based on the quantum state. So I'm wondering if it is an objection to kind of the assumptions that you make, or that account that you give, to bring up facts that are probably true facts that are just kind of over and above what quantum mechanics can say something about, like, like the fact that Bertrand Russell was born before 2000 or whatever. How do you, are you kind of saying that there are two different epistemic frameworks, one that applies to quantum mechanics and one for, normal life, or how would you respond to that?
Yeah, so that's a very good, very, very philosophy-oriented critique. So I guess the easy way to respond to that would be to say something to the effect of, if we take quantum theory to be like an absolute true description of reality, then there would exist some conceivable explanation in terms of the Schrödinger equation applied to a sufficiently large, complicated quantum system that would entail, with some probability, that Bertrand Russell would have been born on a particular date, and so on, and that somehow our talk of those things is really some sort of coarse graining of what are fundamentally microphysical facts. Now, that's of course like a contentious thing to say, right? But if you I think it's fair to say that we take high-level facts in most kinds of theories to be to have realizers amongst facts of more fundamental theories. Now, the extent to which high-level facts form, for instance, natural kinds over, microphysical facts is, of course, a hard question for the people who study theory reduction to address. But I think that as long as you're not talking about things that we take to be true or false or knowable or unknowable about the mind, I think that you can give a compelling argument that if it's something that can be described by some sort of scientific theory, then there is in principle a way out of saying that this could in principle arise from quantum mechanics in some way. Now, that's not a very satisfying answer because there's a lot to be filled in about how that reduction would work. The other option, of course, is just to say, well, yeah, if all of your knowledge comes from quantum mechanics, then it's going to be a fairly prohibitive definition of knowledge. Maybe what we end up with is a definition of knowledge that describes knowledge obtained about quantum systems by quantum agents. And maybe we need another theory of epistemology to describe different kinds of knowledge in different settings. And then there would be a question of what would that look like? How would the two talk to each other? What would everything look like all at once? And that would definitely become a more frustrating problem to address. Yeah.
Okay, thanks. Yeah, it's interesting.
So let me jump in. I always have trouble keeping track of different acronyms and names for different axioms. So I was curious just to hear even one example. Let's say, suppose I'm an adherent of the relative state, so-called many worlds interpretation of quantum mechanics, right? Schrödinger equation only. Which axioms does this lead me to have to throw into question?
Sure. So so this is actually a really interesting point, and many worlds is a very good example of an interpretation that has led to some contention in the literature about this. So in the context of the Frauchiger-Renner assumptions, there's kind of two options that are available to the many worlds advocate. One of the options is to deny the single outcome assumption and to say, actually, there are instances where multiple outcomes do genuinely happen. There are instances in which there is reality behind both detectors clicking. And there's a picture that seems, at least on the surface, to be compelling about that. Something that's certainly uncontested is that the many worlds framework definitely allows the Q assumption to be sustained, because many worlds is on most ordinary articulation.
What does Q mean again?
Oh, the Q, sorry, yeah. The Q assumption is just to say that the Born rule is like you're allowed to reason using the Born rule. And for the many worlds theorists, the Schrödinger equation and the Born rule are pretty much it. That's pretty much what is there. I mean, okay, there's.
Or you could argue that the Born rule is the hardest thing to understand in the context.
It's the hardest thing to understand, but they would still take it to be descriptive and something that they're allowed to make use of. But this question about single outcomes is interesting, because I think if you take many worlds seriously, you actually don't violate the single outcome assumption, because on a more nuanced reading of many worlds, it's not the case that multiple detectors click. Rather, it's the case that agents that are causally separated from each other in different branches of the wave function observe different outcomes. But there's a sense in which indexing those outcomes by the agents that observe them requires us to keep track of different agents, right? There's a sense in which if I flip a coin, the version of me that sees heads and the version of me that sees tails are no longer the same agent. And what ends up happening here is, okay, there's no individual agent, that is to say, no agent that is individuatable from other agents sees multiple outcomes at once. But what does happen is there then become agents that are causally separated from each other, that if they were to
believe contradictory things.
Mm-hmm. And so then the C assumption gets violated, because they can't infer things from each other's knowledge. Yeah.
And what about Bohmian mechanics?
Okay, so the Bohmians have a whole other way of responding to the Frauchiger-Renner scenario. And one of the ways that they do that is they say something to the effect of, by partitioning the world into distinct observers and distinct laboratories to begin with was a mistake. So they say, well, there is only one quantum system, and it's described by this, this single pilot wave, and that's it. So if you're talking about, for instance, the lab that Alice occupies and the lab that Bob occupies, and Ursula as a physical system studying Alice's lab and Wigner as a system studying Bob's lab, they would kind of say, well, it doesn't make sense to call these all different things. These are all just like different components of the same state. This is all one system. And to partition it into other systems is a disingenuous use of the framework.
And what does that do to Fitch's paradox, though?
So I think that I'm kind of inclined to think that if you really want to take, if you really want Bohmian mechanics to get to be something that you can take seriously, there's actually a lot of work that you have to do to show that the Q assumption is sustained. For instance, like this view of like normal distributions as being the right way to describe our uncertainty about the deterministic state of the pilot wave and so on. And there is enough contention in the Bohmian communities, I think, to argue in principle that they could also have to give up on the Q assumption. And in that respect, there would be a possibility for them to deny Fitch's paradox. Another option would be to say something to the effect of Fitch's paradox. It's no longer clear what an agent is. If you're a strict Bohmian in the sense of there being only one physical system whatsoever, am I the agent? Are you the agent? Are we both collectively part of the agent? I think describing agency becomes a very difficult thing for the Bohmian, and for that reason, they might still face Fitch's paradox, but it's not clear who faces Fitch's paradox. Yeah.
Thank you. Other questions?
I have a last question, which is, so I don't remember all the details of the FR scenario. I don't remember their last names, but to what extent are the results, or to what extent is quantum mechanics necessary for those strange results? In other words, like, could I cook up some Markov chain that produces similar weirdness? And as a corollary, if I simulate that scenario on my laptop and produce the same results with the exact same statistics as quantum theory would expect, can I make the same philosophical claims, or is there some step there that's missing?
Right. So this is a good question. I don't personally know okay, there's a whole framework that a lot of people in quantum foundations are very interested in right now of generalized probabilistic theories, GPTs, and more general issues of resource theories, and how you can look at things like extensions to quantum theory and different kinds of non-classicality that don't appear in quantum theory but appear in other toy theories and things like that. And you end up with people generalizing a lot of results that are traditionally from quantum foundations to be applicable to very broad classes of theories that are not just quantum theory. So, for instance, there's notions of, like, you can write down Bell inequalities. There's a thing called the PR box and box world, which is a whole hypothetical world governed by a hypothetical theory with certain correlations, where you can actually violate Bell inequalities that are stronger than those of quantum mechanics. So there's like,
but I suspect you're going in the opposite direction from Noah's question, because we can devise theories even weirder than quantum mechanics.
Yes.
I think what Noah's asking is, within a classical probabilistic theory, is there any way to get a Frauchiger-Renner paradox?
Yes. So the way that I would want to get to that is to say, there has been some work to generalize the Frauchiger-Renner paradox to broader classes of theories, and I think there are some results about how it would look, for instance, in box world and things like that. But one important feature of it is that you really need superposition. Like that's kind of a necessary ingredient. And there's also, I think to an extent, entanglement also becomes a very important thing. And I know that there's resource theories of superposition, resource theories of entanglement that show that if you don't have access to certain kinds of quantum mechanical resources, those are not states that you can prepare. Those are not the kind of thing that you can even see in a world where you don't have access to those resources. And consequently, if you are in a world that's governed by classical physics or just classical stochastic processes, you wouldn't. I'm pretty sure you wouldn't be able to write down this protocol. You wouldn't be able to build a lab with the kinds of resources necessary to create the relevant interactions. And another thing to say about that is,
but I can simulate it on my laptop. So what's the philosophical objection?
Yes, so you can simulate the evolution of quantum states on your laptop, and that's perfectly fine. But there's certain senses in which that's fine, and other senses in which that's less fine, depending on how far into quantum computing you want to go. But if you are able to simulate these fairly simplistic states, these are qubits doing fairly easy things. What you get is you get certain relations between pixels on a screen, right? Or more correctly, between certain parts of your memory and your computer that end up being interpreted as pixels on a screen. And for that reason, it's not really kind of what you're doing is you're simulating a quantum process, and claims made about knowledge for the agents that are found in that simulation would only be true in the context of the simulation. So there wouldn't actually be a physical agent that's experiencing these sorts of things. Rather, there would be a simulated agent that would have these kinds of, there's no actual mind in the world that's getting knowledge of any physical system. There's kind of a hypothetical simulated non-real agent that has hypothetical simulated non-real knowledge of other hypothetical simulated non-real systems.
There won't be any contradictions about our knowledge of the states of different transistors in our computer or anything like that. Yes.
And if you were to look at the states of if you were to write down classically some description of your computer, you wouldn't find at the level of basic physics, basic classical physics, you wouldn't find this kind of contradiction showing up. It only comes up when you interpret the language that's being encoded in the bits on your computer, the classical bits on your computer. Once you interpret those in a particular way, only under that interpretation does this kind of problem appear. Does that help?
Yeah, that does. That's actually a really good answer. Thank you.
Great answer. And I think Noah prefaced it by saying a last question. And I think given the time, that's probably fair. So let's all just thank Patrick again for bringing natural philosophy back together with unnatural philosophy. And we all enjoyed it. And it was very thought-provoking. Thanks a lot, Patrick. Bye.